What is it? Do you want me to shut off that light?
Yes, please.
Where was that?
I think it's over there.
Oh.
Yes.
Is that better?
Yeah, definitely.
So what we'll do first is just kind of set things up here. And so we'll have our coordinate system like so. We've got X, and of course we're using the complex plane, so we've got JY here. And let's draw a ground location here. And let's go ahead and draw some body that is rotating about the ground. And so what we do here is we go ahead and let's look at a point A. If we draw a vector up to that A, we already know what we can call it from the position analysis perspective. And that is our A. All right, so we're going from O to A, so I don't have to include the O in that subscript, so it's just RA. And we put a line under it to denote that it is a vector, position, and magnitude. So say if we have the body rotating like that, and we label this, this is body 2, so we'll label that omega 2. So that is the angular velocity. So let me ask you, if I'm focused on point A here, and my omega 2 is going like that, what's the linear velocity of point A? Is it going straight up? Going like this? Going like this?
Is it normal
Like
to?
this? So why are you doing that? Why are you saying it's going like this?
Is it the normal to?
Because it has to be normal or perpendicular. Okay? So it has to be perpendicular to that. So what we do here is we note that this thing here is going like this. So that is the velocity, linear velocity of point A is going like that. So I want you to note here that if I have this thing here as theta A, then this angle right here, if I just kind of transpose the axis up to here, this angle right here of the velocity of A is simply theta A plus 90 degrees. All right. And so what I'm going to do is I'm going to put some unit vectors down here. So this unit vector down here, this unit vector here is e to the j theta A. So if I take this unit vector here that's perpendicular to it and in the direction of the velocity of A, all I need to do to rotate that is stick a j out in front of it. So it's j e to the j theta A. So that's the unit vector on that right there. All right. So I can write that RA equals RA, so I'm just going to write the magnitude of that, no line under it, and it's multiplied by e to the j theta A. And for the velocity of A, I can say that that equals RA. Well, tell me what the magnitude of this vector is. What's the magnitude of the velocity of A? It's omega 2 times RA, because what you do is you look at the angular velocity, see how far it is out from the center, multiply those two things together, and you get the magnitude of it. All right? So this thing here is RA times omega 2. Now, we know the direction is simply J e to the J beta A. So that's how we're looking at this thing here. So I'm going to say that omega 2 equals the change of theta A with respect to time. All right, so again, this is the angular velocity of link 2. That's why we put the 2 here, because we're referring to the angular velocity of link 2. So the velocity of A equals the change of that position vector with respect to time. All right. And so using the chain rule on this, I can say the derivative of RA with respect to theta A d theta A dt. Well, note that omega 2 here is, we already wrote that, is d theta A dt. So this thing right here, this is what this is. Okay? So what I do is I look at this right here. I'm going to look at this part right here. And this equals the derivative. Let me write the whole vector here. RA e to the j theta A. So if I look at this here, this simply equals, if I just take this, all I have to do is drop the j down in front of it. So this is the j, drop that down. RA, and that's times e to the j theta A. So that's why earlier when we did that Euler notation with these e to the j things, that's the reason why we did that a couple of weeks ago. It looked kind of awkward or cumbersome when we first did it, but there was a reason behind it, because I knew later on I was going to take the derivative, and it's really easy to take the derivative of e to the j theta A, because all I have to do is drop down the j. Yes?
I just put together what you did.
Okay? You good?
Yeah.
All right. So let's rewrite this thing here. So what I did up here is I kind of showed you, hopefully I showed you the steps behind it to write that equation. And now I'm just doing it via math, just to kind of prove that what we thought intuitively up here, I'm proving via math down here. So the velocity of A equals J, so I'm just going to take this thing here, J, RA, e to the j, theta A, and I'm going to multiply this times omega 2. All right, because this part here is your omega 2. So let me write the conclusion here. It's J,
Can you
RA,
move the differ up?
omega 2, e to the j, theta A. I'll box that in. And that is the polar form. And the Cartesian form is the velocity of A equals RA omega 2 times minus sine theta A plus J cosine theta A. So that right there that is the Cartesian. let's talk about this, this J here, I'm sorry, omega. So if I draw my low coordinate system again quickly, X here, Jy here, and I have my little kidney bean rotating about the ground here. If I say that we have omega going this way, that is a positive omega. And if we have omega going this way, that is a negative omega. All right? And so if I write this thing here, the plus omega here is a positive rotation counterclockwise, right hand rule. And I'll abbreviate this RHR. What I mean by that is you take your right hand and you curl your fingers in the direction of your omega, and if your thumb is sticking out of the plane, that is positive. So, and likewise, if you have the negative, that means you have a negative rotation, and it's clockwise. Okay? So again, take your fingers and wrap them in the direction of your omega, and if your finger is sticking into the plane, that means it's the negative direction. So into the plane is negative, out of the plane is positive, and use your right hand in order to determine that. Okay? The other thing I want to point out here is the JRA implies that it's perpendicular to the position vector RA. And the RA omega 2 is the magnitude, which is simply the radius times the angular speed. Of point A. So it's the magnitude of the velocity of point A. Okay? So that kind of finishes my intro to velocity analysis. Now we're going to look at how we can do this graphically, and I'm going to introduce this thing called instant centers. They're called instant centers, or I'll say ICs of rotation. And this is a way, instant centers are a way to determine the velocity of points on mechanisms using this graphical approach. So rather than apply the tool at first, what I'm going to do is I'm just going to show you how to find instant centers on mechanisms. After I show you how you find them, then we're going to see how we can use those to determine graphically velocity. So let me draw something here. So I have this shape here, and say if I have point A here, and somehow I'm able to determine that this point A has a velocity that looks like that. All right? Then let's say I have a point B here, and point B somehow I'm able to determine that its velocity looks like that. Okay? So based on this right here, if I wanted, so if I look at this thing here, and at this snapshot, or instant in time, I see the things going like this, where do you think, first of all, do you think it's moving in a linear fashion, or do you think it's rotating? It's rotating, right? And so it's rotating about some center. Where's that center? Do you think that center is up top here? Where do you think it is?
Below the thing.
Yes, it's below it. And how you find out where it's below it is you just drop these perpendicular lines off of your velocity. So this right here becomes your instant center of rotation. Now again, instant means snapshot, or just that snapshot in time. As the thing is rotating, now it moves, say, over here, well, your instant center changes. So you can track it, if you wish. All right? But as the name implies, it's just at that instant in time, the center of rotation. So we could actually look at this, and we could measure this vector up to here, which is RA, that distance, and we know that this one here would be RB. And I can say the magnitude of velocity of A, not the line under it, is equal to RA times omega. And so therefore, omega, in this case here, is moving like this. So here's your omega. And your velocity of B equals RB times omega. All right? So if you want to, you could say that omega equals the velocity of B divided by RB, which also has to equal the velocity of A divided by RA. So we get these relationships here that we can use to our advantage later if we wish to. All right, we will. So that is what an instant center is. So let's look at another case here. Say if we have a sliding block. So we have a sliding block. It's pure translation. Okay? And if I pick a couple points on the sliding block, if this point is A, I know that the velocity of that, say, is looking like this. So this is a velocity. And then say if I pick another point, say here, and I'll call that point B, I know that its velocity will be of the same length and the same direction as A. Okay? So this right here, let me put a line under it to denote it is a vector. Okay? So for pure translation, for pure translation, VA equals VB, both in magnitude and direction. So applying our instance center methodology here. So let me just drop these lines here. So I'll drop a line here, I drop a line here. Okay. Where do those lines intersect? They don't. How about if you're a math major from the college? Major, yeah. So the professor in McComb would say, no, 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 they intersect, those parallel lines intersect at infinity. Okay? So these are parallel lines, right? And I've never walked that far, but I've been told that parallel lines intersect at infinity. Therefore, the instant center is a point at infinity on any line that is parallel to these lines. And that's an important note that we're going to apply later, so just kind of keep that in mind. So we did a sliding block. We've done something, you know, that's kind of rotating like that. We've done a sliding block. Let's do this right here. Say if I have a circle, all right, there's the center of the circle, and say it's rotating on a plane here, okay? So we know that this is ground. Yeah, sorry. So we know that this is ground, and this is body 2. And we have two bodies here, ground and the rolling disc. All right. So where do you think the instant center is on this one right here? Do you think it's here?
Yeah.
I would think so too, but it's not. It's right here at the point of contact, okay? So this right here is your, that point of contact. This is the IC of rotation, or this disc here. All right. And so now we're going to introduce some notation here. So this is what we call I12. It's the same thing as I21, because you look at these things, if I'm standing on body 1 looking at 2, it looks like it's rotating like this, so it's I12. But if I was on body 2 and I was looking at ground, it looks like the ground is kind of rotating, even though it's not rotating. So what we do is we try to always keep the smaller subscript first. So I don't write it like that. I write it with a smaller subscript first. Just because it gets a little confusing if you start swapping the subscripts. But indeed they are equal to each other. But we're just going to write the smaller subscript first. So let's do another one here.